Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to the next lecture of CS131 Discrete Structures, where we are talking about trees. This is chapter 11 and section 11.5 that we're going to go start talking about. So far, what we have seen is basically some of the basic introduction to trees, and we have seen applications of trees as well. In particular, you saw the different notations that are associated with trees, and you have seen the Huffman encoding problem and some other applications of trees as well. We then talked about the tree traversal, and we have also talked about spanning trees. And spanning trees, as I've said earlier, are basically trees that we can get from the underlying the undirected graphs or even from directed graphs, where basically different algorithms that are present. And we saw how we could apply the depth first search and the breadth first search techniques to get the trees from it. However, in this lecture, in the current lecture now that we're going to see, we're going to talk about the concept of minimum spanning trees. And we'll see again two algorithms that can be used to determine the minimum spanning tree. This is something which is kind of shortest spanning path problem, where we use Registra. We'll see some algorithms that are very similar to them, but maybe how to get a spanning tree, how to get a minimum spanning tree from a given graph. That would be the topic of Prim's and Kruskals algorithm. So let's start with the lectures, and this is the last lecture of section 11. So after this particular lecture, we are done with the chapter 11, and we'll then start off with chapter 3 after this, which will be about complexity of algorithms. So like the name suggests, we are going to talk about minimum spanning trees in this particular section. And a minimum spanning tree by definition is in a connected weighted graph. So now we have a graph that is a weighted graph. Is a spanning tree that has the smallest possible sum of weights of its edges. So in that sense, when you're trying to find the minimum weights to traverse a graph, it's in the same way. We now want to find the minimum spanning tree, which is which has the smallest possible sum of weights of its edges. So it is a spanning tree that has the smallest possible weights of edges. That is the game here. So how do we construct minimum spanning tree? Well, we'll present two different algorithms for constructing minimum spanning tree. And this is really easy. This is easier than the Dijistra's algorithm that we've seen in the previous lecture, actually. So, but there are two different algorithms that differ slightly in their mechanism. Both were made almost at the same time, unknowingly, by two different persons, but both have found a widespread application in trees and in construction of minimum spanning trees. So both proceed by successively adding edges of smallest weight from those edges with the specified property that have not yet already been used. Although both are greedy algorithms, and a greedy algorithm by definition is a procedure that makes an optimal choice at each of its steps. Generally, and that's generally true, I mean, optimizing at each step does not guarantee that the optimal overall solution will be produced. However, both these algorithms that we're going to present in this section for constructing minimum spanning trees are greedy algorithms that do produce optimal solutions. So the solution that is produced by them is an optimal one, and that is a rarity actually for greedy algorithms, but in this case it is true. So let's talk about the first algorithm, which is the Prim's algorithm. So the Prim's algorithm begins by choosing any edge with smallest weight, putting it into the spanning tree. So it first selects an edge with the smallest weight. Then the next thing it does is that it adds to the tree edges of minimum weight that are incident to a vertex already in the tree. So of course, when you add an edge, it will have two vertices. And for both the vertices, it will then select the next edge, which has the minimum weight. And and another thing is that you will add an edge if it does not form a simple circuit with those edges that are already in the tree. And we stop actually when n-1 different edges have been added to the tree. So this algorithm will produce a minimum spanning tree for any connected weighted graph. Here's the whole algorithm itself. So the first we start with T, which is a minimum weight edge, right? So it just contains a single edge. For I is equal to 1 to n-2, where E is an edge of minimum weight that is incident to a vertex in T. So it is there is a vertex in T, and you're basically getting an edge with the minimum weight. and not for and that adding that edge should not form a simple circuit in T if added to T. And finally, what you do is you basically add that edge to T and finally return T, which is the minimum spanning tree of G. So let's say if we want to use the Prim's algorithm to design a minimum cost communication network connecting all the computers represented by the following graph. Let's suppose that we start at Chicago, right? And we determine, in Prim's algorithm, we actually determine the edge that has the minimum weight. So the edge with the minimum weight in this particular scenario is probably this 900. So San Francisco from Denver is my first choice, right? Yeah, even less than that is the cost over here. Chicago to Atlanta should be my first choice. So the first edge that I should select is from Chicago to Atlanta. So Chicago and Atlanta are my two vertices. And next one, I need to add the one which has lowest cost that is connected to these two. So from Atlanta, I can basically go to here, go to here, go to here, right? So the one with the minimum cost is this 800. From Chicago, I actually have got 1000, 1300 and 1200. Again, between all of these choices, this one, since I've used this edge already, right? So if I can use a marker here. So I've used this edge, selected these two, Chicago and Atlanta as my first choice. Then the next edge is possibly I've got options of choosing here, 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 or here. Of course, this one is the least. So next one is Atlanta to New York. Then the next one is probably from New York. I can go to by using 2000 to San Francisco. From Chicago, I can go using 1200 to San Francisco, 1300 to Denver, right? And from Atlanta, I can use 1400 to Denver or 2200 to San Francisco. So the next choice is basically this one, right? With using this edge. And then the next choice now is I can actually go to Denver using this. So this is then the smallest one, and I'll use this one to reach Denver. And then all my nodes have been visited, and that's my final answer. So the edges that I'm going to use here are these ones. The cost of it is going to be 700 plus 800 plus 1200 plus 900. And that's the final cost. And we can see this is the exact nodes that are chosen, and the final cost is 3600. Excuse me. So now we notice that these are the edges that were used ultimately, and in the same order: Chicago to Atlanta, Atlanta to New York, Chicago to San Francisco. And here the vertex that is nearest is important. It's not that you just choose the one with the lowest weight, but actually you choose the one with the lowest weight that is connected to one of the vertices that have been visited, and you don't want to create a tree again. That's the main thing here again. So let's take another example of Prim's algorithm. We can use Prim's algorithm to design a minimum cost communication network connecting all the computers represented by the following graph. So this is the graph. And in this case, we can actually start from an edge BF. BF, if we note, has the lowest weight. So this one, this edge has the lowest weight. We can select this one. That means B and F were selected. In the next step, we next can select basically AB with weight 2. So this, since this has the second lowest weight, we select A, right? Then this one is the next one that is connected and has a slowest weight. So we can next select FJ with 2. Then we basically can select weight 3. So with weight 3 that are neighbors, we actually have got 4 options. We have got this option, 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 right? So let's start with, let's say, IJ, let's say AE. So it's first selects this one. So AE is selected. AE is selected with this weight. Then it selects IJ. IJ, this one is selected. So I is also done, right? And then it selects FG as its next one. So when FG is selected, you actually have got another weight that is of weight 2. So this one will be automatically selected next, right? So FG gets CG. And then finally, you have got a JK. No, JK is not selected here. Okay, with FG, it then selects GH, I think. So with FG, with C, it then selects CD. Because it has got a weight of 1, so that has the lowest one. So this one gets selected. Then it selects GH with weight 3, then HL of weight 3, and finally K with weight 1. And this is kind of guaranteeing that, you know, we select the ones with the lowest weights. Okay, so the total here is 24, and the reason for doing that is that it should not create up a in this particular algorithm, it should not create a cycle, number one, and number two, we don't want to use a vertex that has been visited already. So then we talk about Kruskal's algorithm. Kruskal's algorithm is slightly different from Prim's algorithm. In this case, we choose an edge in the graph with minimum weight. Then we successively add edges with minimum weight that do not form a simple circuit with those edges that are already chosen. So in this case, the difference is in terms of Kruskal's algorithm is that we'll always choose an edge with the lowest weight, regardless of, we are not looking at the connections with the already selected vertices at all. And we stop after n-1 such edges have been selected. Kruskal's algorithm produces a minimum spanning tree for every connected weighted graph, right? So again, it's the same thing. We start with an empty graph as our tree, and finally we keep on adding any edge with the smallest weight that does not form a simple circuit when added to T, and then T is, we add just an edge to the T and turn this tree. The reader should note the difference between Prim's and Kruskal's algorithms. In Prim's algorithm, edges of minimum weight that are incident to a vertex already in the tree and not forming a circuit are chosen. Whereas in Kruskal's algorithm, edges of minimum weight that are not necessarily incident to a vertex already in the tree. So in this case, that are incident to a vertex in the tree, right? And in the second case, that are not necessarily incident to a vertex in the tree. However, the other conditions is exactly the same, that do not form a circuit are chosen. Note that as in Prim's algorithm, if the edges are not ordered, there may be more than one choice for the edge to add at the stage of this procedure. Consequently, the edges need to be ordered for the procedure to be deterministic. And by deterministic, we mean it should reproduce the same result every time. So let's take the same example. Let's find the minimum cost. In this case, the one with the minimum cost is again this edge, right? So this will be added first. Then this edge is going to be added next, right? And once you add an edge, you're basically going to use up this one and this one and this one, right? And this one and this one will be the first three that will be added. So note the order here. The order here is very different from the Prim's algorithm. And that's the exact case. So this one produces them in the order of their weights. And that's the final result. So if we just focus on the final result here, this is in order of weights. While if you go back and discuss the Prim's algorithm, the Prim's algorithm here, it's not by order of the weight, but again the edges, same edges are being chosen, right? And this kind of guarantees that the edges that are chosen are the same. However, the order may matter or may be different from both. And thus although the result is slightly different, the order is different, yet the result is exactly the same, and both are greedy algorithms. Both basically guarantee optimal choice at each step. However, in both of these algorithms, we are also guaranteed to find the optimal solution. So with that, the lecture on chapter 11 comes to an end, and I'd like to thank you all for listening to the lecture series in particular. So we have discussed trees in detail. We talked about some basics of trees in this lecture. We talked about different terminologies related to trees. We talked about different applications of trees. In particular, I discussed the Huffman's encoding problem and how binary search trees can be used for different decisions. And we saw a practical example where it was applied as well. Then we talked about the tree traversal problem, where we talked about how to traverse trees, and then notations of different trees. For example, the prefix ordering, postfix ordering, and the infix ordering that results in infix notation, postfix notation, and prefix notation. And then we talked about spanning trees, so trees that we can get from underlying graphs. And we saw some algorithms here called the breadth first search algorithm and the depth first search algorithm that are very important for a lot of your different lectures. We then talked about a little bit about the minimum spanning trees, and in particular, we talked about the two algorithms, the Prim's algorithm and the Kruskal's algorithm. And both of them, we saw an application, we applied them to a particular problem. So that brings to an end chapter 11 of your book. We'll now start with chapter 3, which is complexity of algorithms, in the next lectures. So take care and Allah Hafiz.